All right, so a bit of a fast one today. I'm going to be talking about the concept of Gauss's law this time around. Um,
hmm
and then next class period, we're going to be going through the calculus behind it. So this will be two parts. Again, I'm stealing all of these slides from Bull's Physics with permission on his website. Okay, so before I can talk about Gauss's law, we need to talk about flux. So if we were to define an area of an object like this, and then looked at the amount of electric field lines that were passing through it, then we could say that the flux is the area that has that electric field passing through it. And you can think of it as like flow. This is how much electric field would be flowing through it, even though nothing's actually moving. Remember, field lines are what would happen if you dropped a point charge at that point. It's all the forces that a point charge would feel at that point, right? Um,
hmm
so even though nothing's actually moving, the force exerted by your charged object is creating all of these possible forces, these field of forces around an area that we could define. So the flux is just how much of that electric field is passing through that area. If we defined an area vector as perpendicular to the surface of a material, um, then the area vector and the electric field vector would be parallel. So that gives us a dot product between the two variables that gives us flux. So our electric flux then, even though nothing's moving, is sort of like the flow of these electric field lines through a surface area, which we can model with the dot product. Your electric field dot area. If I was going to take the infinitesimal, the infinitely small flux, which we could represent with, I've actually forgotten my Greek letter. I believe this is phi. Um, if we take the infinitely small change in flux, then that would be the integral of our electric field times our infinitely small change in area. So we could integrate over the entire surface. If you see this little circle inside the integral, that just means you're integrating in an enclosed space. It doesn't actually change the math at all. Okay, so visually, on the left, my total flux for this shape would be 0 because I've got the same amount of fields coming in as I do coming out. But on the right, my flux would be 2 because we've got 1 in and 3 out. So our flux total could be positive or negative. If I take a look at a cylinder, if I wanted to figure out what the electric flux was through the cylinder, then we could sum up the flux on each of the different surfaces that are presented. So if I've got maybe a charged rod or a charged wire, what we'll be dealing with, a bunch of point charges in a line, then I can model the electric flux with a cylinder that goes around that line. And what you'll find is your total electric flux ends up being 0 because the surface that is here on surface 3, rolling around, ends up being the cosine of 90 when we take the dot product, which is 0. And then on surface 1 and 2, because they're both in opposite directions, they'll cancel out. So our total electric flux ends up being 0. So if you think of like a river flowing, the water is coming from a spring. So your spring would be the source of flow. If you were to enclose that spring, so where all the water is coming from, with a closed surface, and just let the water build up, then the total flow out of the sphere, so out of that imaginary sphere that we've created around our spring, would be equal to the rate that the spring is producing water. How much water you put outside your imaginary sphere is the same amount of how much water is generating inside, right?
Mm-hmm.
Okay. What Gauss's law is basically the same idea. We're going to sum up the total amount of flux through the surface, how much electrical force is flowing outside this imaginary surface area, to figure out how much total force is being generated on the inside,
Mm.
or vice versa. We know how much total electrical charge is contained within this sphere, and we can use that to figure out at any particular radius away from that sphere how much electrical force would be flowing through that surface area. That's Gauss's law. The total sum of the sources within a closed surface is equal to the total flux through the surface. One other thing to consider is that different materials that you're sending this force through will have a different amount of permittivity of your force, which just means it might be harder to transfer your energy if you're moving in water or air versus in a vacuum. So we represent that with a constant of proportionality, represented as epsilon, which in this case means the permittivity of free space, or a vacuum. If you were to suck all of the area outside of your experimental area, suck all the air out of your experimental area, then how much permittivity, how much a vacuum with no air in it would allow your energy to flow is based on your constant of proportionality, epsilon.
Mm.
So you could say our flux is our amount of charge that we have enclosed divided by the permittivity of free space. And it's also the integral of our electric field and the dot product of our infinitely small change in area. So for any section on the sphere, infinitely small area, there will be some amount of electric field that passes through it. If you integrate, so multiply the dot product, so how much is acting in parallel to our area vector that we've created, moving outside of the sphere. Excuse me. Then you'll end up with flux. So we can use Gauss's law to model point charges by enclosing a bunch of point charges inside our imaginary sphere and figuring out what the flux is in relation to them. So in this case, if we throw a point charge in and then create a Gaussian sphere around it, then we'd have symmetry all around that point charge. The electric field at all points on the surface would be constant because they're all the same radius away from the charge. So in that case, if our electric field is constant, then I can pull it outside our integral. We could say that our electric field times the integral of our change in area, infinitely small change in area, is equal to our total amount of charge enclosed divided by the permittivity of free space. Since our surface area of a sphere is 4 pi r squared, when we integrate our infinitely small change in area, we would get 4 pi r squared. And since the charge enclosed is q, the amount of charge that a point charge could have, we end up with the same equation that we had for our equation of a point charge last class period that I didn't really explain.
Mm.
Okay, so last thing for today, I think, and then I'll leave the rest for next class period. We talked briefly about what a Faraday cage was. We said if you enclosed a conductor around around a space. So maybe created a giant three-dimensional box that was made of a metal that conducts electricity. Um, then all of the charges that moves on the outside are just carried around the conductor, and they don't affect what's inside. And we can prove that mathematically by looking at our flux. Because our total electrical field that we're sending outside of the surface is now 0 because nothing is passing through the conductor. Instead, it's just carrying around the inside of the conductor. We end up with a total electrical field of 0, which means our total flux is 0, which means if you put something inside the box, you wouldn't be able to carry electromagnetic radiation into it or out from it. Michael Faraday ended up proving this by creating a massive Gaussian sphere, stamping inside it, and then shocking the outside. And he wouldn't get shocked when he was inside, because all of the electrical energy, all of that extra positive charge that he was sending into the box, was instead being carried about the surface and just charging the surface of the box, without affecting what was inside.
Mm-hmm.
Okay. So that's all I've got for today, just concepts. Although we do have a lab that I've just sent through the WeChat. When you open up the lab link, you'll see something that looks like this. So we've got a circuit with a light and an inline voltmeter, but you also have this coiled wire that we've created here. So we're basically creating a massive cylinder within the circuit. And that's creating a lot more surface area that we can affect with our electric field. What I want you to do is when you open up the lab, kind of drag the magnet around, put it in a bunch of different places, and see what makes the light bulb end up burning the fastest. What would you have to do with the magnet in relation to the coil in order to get the light bulb to light?
Oh.
In real life, the current that is going into your light bulb right now in your house is alternating current, which means the voltage keeps moving, positive, negative, positive, negative, positive, negative. And so the light bulb's constantly moving on and off. It's constantly flickering, but it's flickering faster than your eye can see. So we interpret that as light that's constant. And then I've got a handful of questions to answer below. The links that I've included in the document are to, one's a YouTube video about insect wings, and another one is a link from Popular Mechanics, which is a scientific journal that posts new advances in mechanical engineering mostly. But in this case, it's kind of a joint, sort of a biotech research article that I've linked on genetically engineered dragonflies. If you don't understand the question, let me know on WeChat and I can answer any questions you've got.
Mm-hmm.
Okay, any other questions from today?
No.
All right, thank you very much for coming. I'm going to take up the worksheet, we'll say Friday at midnight. After you've had a
So
chance to...
Friday.
Yep. I don't think it'll take that long to work. But I'll take it up Friday at midnight and then we'll talk about it.
Okay.
All right. Thank you very much. I will see you tomorrow.
Bye bye.
Goodbye.